This video is going to look at volumes. Normally for these videos I try to focus on a single node and go into that in detail, but I think because volumes are very complicated and there's a lot of different things you can do with them and you need to use them in different ways, it's probably best if I just do a general overview of how they work and some of the different networks you'd want to set up to get them running. And then at a later date we can go into some of the nodes in detail. So something else I've done slightly differently is I normally like to build my scenes as we go along, but for this one I've set up a scene in advance which I'll share with you. So the scene is called Volumes and it starts off with the Houdini pig's head. So if you're unaware of this, Houdini actually comes with a bunch of test geometry. There's a couple of characters and you've probably seen this in videos, a rubber toy and the squab is a kind of squid and the pig's head, which is my favourite. So let's open it up and you see that I've made a little graph here. Now there are a lot of different varieties of volumes and a lot of the tools for volumes are aimed at SFX and looking at things like steam and smoke, which isn't something we're going to be covering. So what I'm going to do is focus on the uses of volumes in a procedural geometry network, and I'll show you some of the different ways to set them up. I think the reason volumes are so confusing is because there are two different ways of storing volumes. There's what Houdini calls a volume, and if you open up the menu inside an object node, you will see there's a volume menu. So all this stuff is to do with manipulating volumes, and this is the original way of working with volumes in Houdini. However, since then, but still quite a long time ago, Houdini also adopted the VDB format, which is it's a way of storing volume information that very generally doesn't store information for empty points or voxels. So it's cheaper, particularly if you're working with large scenes. Unfortunately, the way that volumes and VDBs are worked upon by nodes is slightly different. So although some nodes are common to both, not all nodes are. So it starts getting quite complex. To add further complexity to it, within each of these there are two ways of using volumes. So you have what's usually referred to as fog, which is a volume where each point or each voxel within the volume stores a numerical value. So if you imagine a cloud or some fog that has thicker areas, so they would have a higher value, and thinner areas. You can also use this to store vectors which are used in special effects such as smoke. But there's also another way of displaying volumes, which is to again give each point a value, but this time it uses a surface and it gives you the distance. Each voxel has a value that tells you how far inside or outside that surface it is. And the two ways of holding this information are useful for different types of things. So basically I'm going to go through all the types and show you some of the most common uses you might make of volumes and look at the most straightforward way to do this. I'll also print this out into a sheet so you can refer to it quickly until you get the hang of it. So first of all, let's take a look at our pig's head. So we're working in something that will probably become procedural geometry here, so we're going to start with a polygon. It is possible to create real volumes from scratch as well, which is something we might go into later. Now, in the traditional volumes, we have our SDF volume. Now, the SDF stands for signed distance field, and that is when we're looking at the distance from our surface. It's called signed because it can either be inside or outside the surface, so it can be a positive or a negative number. When it's displayed as a volume, you'll see there are little points which approximately reference voxels. However, it's hollow in the middle, so to some extent it's very similar to polygons. The other way of displaying it is as a fog volume, and you see this looks very different. So each of the points inside the volume has a different value to say how dense the fog is. If we go to our VDBs, we get the same thing again. So here we have our VDB fog, and here we have our VDB signed distance field. In this case it's referred to as a distance VDB. Now, I'm afraid I've just made something sound very complicated, which I'm trying to keep as simple as possible. So, a simple summary of what I've just said is that there are essentially two kinds of volumes. There are fog, which stores values per voxel, and there are signed distance fields, which stores the distance from a surface, which gives you something more like a surface. And for each of these there are two ways of compressing them, volumes and VDBs, and you just need to be aware of what tools you want to use and what works with each one. Now I'm going to go through the actual nodes that you would work with these. So when you're working with volumes, rather unintuitively, the way that you would create this from a polygon is using an ISO offset node, and you can see we have a list of potential uses here. So we can, let's switch this on. If we put on an ISO surface, we're basically converting it to a volume and back again, and maintaining our polygons. It can be a nice shortcut if you're wanting to get a nice smooth object. You can change the offset, which will move it inside or outside of the surface. Generally I'd rather do this myself, so actually turn it into an SDF volume and then convert it back to a polygon manually and have a bit more control over it, but it's a useful shortcut. And then we have our fog volume, which I've looked at already, our SDF volume, which is our signed distance field, and there's also an option for a tetramesh. The tetramesh is generally used for creating collision volumes. It's probably not something we're going to be looking at for a while anyway. So let's put this back to our signed distance field. The offset will take you inside or outside the original surface. It's pretty straightforward. The mode, there are a variety of different ways of calculating where the surface is. Most of the time ray intersect will do. If you're working with metaballs, it's recommended that you use metaballs because it calculates it slightly differently, but for most of the time we'll use the ray intersect. The other thing that's probably the parameter you're going to change most is the div size. This is, if you like, the size of each voxel. So we can make this smaller and we'll get a more detailed representation of the surface. So our fog is exactly the same ISO offset again, and this time we're using a fog volume. If you at any point are confused about whether you're working with volumes or VDBs, there's a nice easy way to tell. If you middle mouse click on your node, you can see, I can't point to this, yes I can. So you can see here we actually have one volume, and the volume is a component of this object in the same way that any other component is displayed. If we have a VDB, we do the same thing. You'll see that we have a VDB here, and this can be really useful to check on because it's quite easy to switch backwards and forwards between the two, and you can get confused about what you're actually working on because, as you can see, the two look quite similar. So if you want to create a VDB, so first of all you might want to know why you would want to use volumes or VDB in different circumstances. I find 90% of the time I use VDBs. You've got a little bit more control, as well as the file format being a bit faster. There are, at least I seem to use more nodes that are applicable to VDBs. There's one exception, which is what I'm looking at. I think it's here. Though if you're creating points from your voxels, which is something that is a great use for volumes, is to be able to scatter points inside them. I find that the way they're created from a volume makes them easier to deal with than a VDB. So I'll come back to that in a minute. So most of the time I would be working with VDBs. The node for a VDB is a bit more straightforward, or a bit more obvious. It's called VDB from polygons. So that's basically doing the same thing as your ISO offset, but it's creating a VDB. And a lot of the settings are very similar. The voxel size, again, is the size of each of the points inside your volume. And that was 05. We have two options here for a distance VBD, which is the SDF, the signed distance field, and a fog VDB. It's a bit more explicit in VDBs what the value of each of the points is. So a fog VDB has a value of density, which makes sense, and the distance VDB has a value of surface, which again makes sense, but you can change these, and there are circumstances where you might want to change them. The exterior and interior band voxels are to do with, let's have a look at distance VDB, it's a bit clearer. It's to do with how many of the interior voxels are displayed. So you can see it will change the thickness of the surface. I'm not going to go into much more in detail at the moment because there's a huge amount of this and I don't want to get bogged down in one thing. So here we have our surface VDB, which I think for some reason I changed to density. I'll put it back to surface again. Basically, if you're working on a volume VOP, which is like an attribute VOP, by default it works on an attribute called density. So I was playing around with using it on a surface, and it's easier to change that to density. But most of the time you just leave that as it is. So the most common uses of VDBs, at least as far as I'm concerned, are first of all to take a geometric object and smooth it, so apply a more organic surface to it, which if you looked at my last tutorial on attribute transfer, you'll have seen this is what I did to the tree trunk, which if you've got twisted or not very nice geometry, it's a really nice way of smoothing it out because it will just find the surface for you. So basically for cleanup. And if we have a look here, so this is our surface VDB, and here I've run it into a convert VDB node and converted it to polygons. So if you want to smooth out your surface, you're basically just going from polygon to voxels and then back to polygons again. And then there's some things that you can tweak. The thing that will make the most difference is your voxel size. So if you make your voxel size smaller, you'll get a more accurate surface. There's a variation on this where you're actually taking a group of different objects and merging them together. So if you were taking, say for example, you have a small village of houses that are all separate objects. If you wanted to have that village sitting on a distant hillside in your game, that would be very expensive. A good way of optimizing them is to bunch them all together and convert them to a volume and then convert them back again. And this will remove all the inside faces, and it makes it much easier to reduce the number of polygons. If you've used Simplygon, you'll have seen this happen. They have a process where they basically voxelize everything and bring it into a single mesh. So that would be another use for volumes. The next thing you might want to do is, rather than just converting it straight into a smoother mesh, you can run some processes on it. I'm just very quickly going to look at using some noise, using a volume VOP, and then converting that back again. So it's basically using the ability to turn something into a volume to add some sort of volume-based effect to it. Let's have a quick look inside here. So we have our noise. Pump up the amplitude. Not sure if I've set this up correctly. It's because I've turned off fog. If you're wanting to work with a noise within a volume, you're much better to use fog. Fog, in the same way as an SDF, you can convert a polygon to fog and then back to polygon again. So now you can see that our pig's head is being eaten away by noise, which is quite gory. And you can tweak this in real time. So that's the second way that I would use volumes. There are lots of volume nodes and VDB nodes which you can use to manipulate volumes, which we can look at later. The final use that I would generally make of volumes is to create points, and you can do this with any of the types of volumes. You get slightly different results. So here we're looking at our signed distance field. So we're going from here and using a node called VDB visualize tree, and that's creating some points inside and outside the surface. So if you remember, we have our interior and exterior band voxels, and you can use these points for placing objects on. This is the classic way of creating, say, a Lego model out of a pig, by replacing each of these points with a small block of Lego. Here we have the same thing for our volume pig, except you can see the difference is, instead of it being inside or outside a surface, now we've filled the entire thing with points. And then we have the same thing again, created by a volume, and this is the use case where I prefer volumes. It's quite hard to explain with pig's head because it's quite complicated, so I'm going to show you with a box. So I have a very small box here, and I've divided it into 4 segments, and I'm going to put it on template so you can continue to see it. Now if you take a look at the VDB fog, and in fact if you also look at the inside for your VDB surface, you'll get the same thing. So you'll see that each point has been created on one of the divisions. So the points are sitting on the surfaces. Now if you imagine replacing each of these with a 2x2 or 0.2 by 2.2 block, which is the same size as these, you're not going to be able to recreate this cube because some of the blocks are going to sit over the edge. However, if you do the same thing with the volume, then you'll see each point sits nicely inside one of our cubes, and the whole thing is contained within the original volume, which makes things a lot easier to handle if you're wanting to convert into blocks. Now I'm going to share this file with you, so you can refer to it if you want to go through any of these processes. And I'm also going to quickly run you through each one at a time so you can see some of the uses set up from scratch. The first use of volumes I'm going to look at is using it to group together a collection of objects for optimization. So I've started a new empty scene, and I'm going to put in a file node because I've saved a file that consists of a pile of rocks. There we go. So these were created by dropping lots of rocks together and letting them fall into a pile. If you're in a game situation and these were all individual assets, then while you're walking around this pile of rocks, this could be perfectly acceptable. But once you zoom off into the distance, particularly, let's see if I make them transparent, you're looking at a massive amount of unnecessary geometry there, and it's not very easy to optimize it because you're having to optimize each piece individually. So this is where a volume can be useful. So in this case, as in most cases, we're going to create a VDB, and because we're looking at something that is going to eventually approximate the surface, we're looking at a signed distance field, which is a VDB that focuses on surface rather than volume. So let's create a VDB from polygons. If you're working with VDBs, this is how you would create both kinds of them. So you'll find you use this a lot. And here you can see we've now created a series of voxel points sitting either side of the surface, which gives us an approximation of where the surface is. In order to change the precision of volume, you need to change the voxel size, which can be slightly confusing when you're converting it back to polygons again, because you feel like you should be able to change the precision of the polygons, but you need to go back to this original conversion node. So if we make these half the size, you start seeing the shape of the rocks here. But you can't really judge what you need until you've converted it back again. This is a really straightforward two-step process. So we go from VDB to polygons, and then we create a convert VDB node. Now once you have either a volume or a VDB and you want it to become something else, like if you want to switch between the two, you want to convert from fog to assign distance field. This is almost always the node that you'll use. It has loads of flexibility. You can see it looks pretty straightforward, but if you switch it to VDBs, you'll see that there's a lot of options in here as well to change the type of VDB. So let's, for now, stick it on polygons. So we're taking our VDB that we created and converting it back again to polygons, and you can see immediately that it looks very different because the density of the voxels was quite small. It's munged them all together and we're just draping over the surface of that, and you'll see it's actually hollow inside. Now this doesn't look great, but once you get to about here it starts looking not that different from your original surface, and let's have a look at the difference in size. So the original file is 32,000 polygons and this one is 9,000, so it's a lot more optimal. Some other things that we can look at, there's an adaptivity option when we convert it back to polygons, and that will try to reduce the polygons and keep the edges where they're needed. In this case it's not doing a great job because all the surfaces are rounded, so we actually need our polygons pretty much everywhere, evenly distributed across this pile. So let's just leave that off for now. I tend to prefer to use a poly reduce afterwards because I've got a bit more control over it. The ISO value is the distance inside or outside the surface that we use to build our new surface. So when we're looking at our volume, we're not just looking at a surface anymore, we're actually looking at voxels or 3D points that sit inside and outside that surface. So we can determine which of these we want to use as our new surface. So if we push that out, you'll see it's getting bigger and more jelly-like and more diffuse, and we can also pull it in, which will separate everything. I'll show you in a later example where this might be useful. For now, for this example, we just want it at 0. We want our surface to be in the same place. Something else that isn't immediately apparent is you have a transfer surface attributes option in here, which is like a simple shortcut to what you would do with a transfer attribute node. And the reason it's grayed out is because you need to plug something into the second input on your node. So in order to get this working, we want to plug our file into the second input, and now you'll see this is available. And I'm not actually sure if these have normals. Let's have a look. No, they don't. So what I'm going to do is create some normals using a normal node. And these should make point normals. Yep, so now we have normal values. And I'll plug the output of the normal into here. And now switch on our transfer surface attributes, and you'll see it looks pretty messy from here, but it has in fact transferred the normals. So where the closest normal is actually pointing underneath, you start seeing some darker areas where the light doesn't do quite what you expect. However, if you zoom out a little bit, this starts looking much more like our original pile of rocks. So once again, this is a useful thing to be able to do when you're working on optimization. Now let's go up a level and just save this so I can save it in a file for you. We'll call this optimization. Oops. And we'll create a new geometry file here and take a look at using volumes to fix problems with geometry. I'm going to use pretty much exactly the same example I used in the previous tutorial, really because it's a great example and it's nice and simple to set up. So I'm going to create an L system. And I'm going to use one of the defaults. The L system comes with a bunch of predefined settings which are inside this gear symbol. And the one I'm going to look at is, I think it's the sympodial tree. Yeah, that's it. So this is creating a tree. It uses tubes. So you'll see if I turn the tubes off, you're just getting an outline. But the tubes create a polygon around the object. But you can also see it doesn't do a great job of it. So for example, you're losing ends, so there's no geometry there. You're getting some odd twisting as well. Now let's go straight in and once again create a VDB sign distance field. So we want VDB from polygons. And we want a distance VDB. You can see immediately that we've lost quite a lot of our tree because the voxel size is too big. So let's make this a bit smaller. And now we've got a tree again, but we've lost the base of our tree. The reason for this, if you take a look here, is that it doesn't actually have a bottom. And we're also getting a warning here saying geometry has been converted to quads and triangle, which gives us a hint that the original geometry wasn't actually quads and triangles. The original geometry is saved as tubes, so it's a more procedural way of putting this geometry together. So we can do, it's not actually necessary because it's doing it for us anyway, but we can use a convert node and convert this to polygons. It should, yeah, this will get rid of our error. And then we use a node called polyfill, which will attempt to cap off any holes in the polygons. So, and that's not working. Sticking a poly cap, which for some reason behaves differently to a polyfill. I thought they were the same thing, but obviously the settings are different. That one's set to fill a single polygon. Okay, so we have our ends capped off now, and you see this bit's flattened off as well. So now our volume creation is recognizing this base of the tree as being a contained volume rather than being the thin sides of a polygon. And then once again we use exactly the same convert polygons, or to convert VDBs. And that will convert it back to polygons again. So you can see already it's looking a lot cleaner. This junction, for example, is cleaned up. We're still seeing the twisting, and we're getting some disjointed points around the edges. We can fix this by changing our ISO value. So if we ramp this up just a tiny bit, this is essentially making the input surface a little bit bigger. It may allow us to increase the voxel size slightly as well, which will help to smooth out some of the problems in the surface. So if you're happy with having quite chunky branches at the end, this gives us a much nicer result. Let's see if we can tweak it a little bit more. Yeah, that seems to be holding up still. So there you can see we've solved some of our geometry programs. We could use the adaptivity node again, which I don't. It's possibly doing a slightly better job this time, but it's still not great. Or we could add a polyreduce node afterwards to optimize this. Something else, which I'm just going to show you because it is such a neat trick, is this works really well with Coral. You can probably see from the one I've already made how it would work well with Coral. So let's drop in another L system. And we'll just use the default here, which is just really simple branching into 3 at regular intervals. If we increase the number of generations, we get more branches. Let's go up to 10. So that's starting to look a little bit coral-like. Add a tube, and that will probably do at the default. Again, you see we're getting these not fantastic intersections, but we don't need to worry about that. And we'll hook it up. In this case, I don't think we need the polyfill because the sizes are quite small. Yeah, so now we do the same thing and ramp our ISO value up a bit. And you can see we're getting something that looks a lot like Coral. Slightly low res, so again, remember you can change your resolution by changing the voxel size, and that will give us a bit more detail or a bit more smoothness. Let's go up and save this as I'll call it fixing intersections. If you've done the first tutorial, you might be interested to know that the low polygon trees that are used in that are made using this technique. So I'll quickly run through how they're made. I don't think it's loaded into this. I think I'll need to import that digital asset. Oops. That's our first tutorial. So there's our low poly tree. And if we allow editing, we can have a look at what's inside it. It uses a random seed to generate different trees, so I'll see if I can find something that's a bit interesting with more than one branch. Oops, that was quite good. Yeah, that'll do. So if we take a look inside here, and I'll show you how this is made. So first of all, we create a sphere and we create an L system. The L system is very simple. It just creates randomly a few branches, and it takes our sphere and sticks it on the end of each branch. They don't have much resolution at all, so you get something quite simple. And then we play around with that a little bit and separate it out. So on this side we're removing everything except for the lines that make up the branches, and on this side we're removing everything except for the spheres that sit at the points. So the base of the tree uses a polywire, and it's so simple that there's really no need to rebuild this with volumes, so I've kept it as it is. It's quite nice clean lines, so that's used for the final tree. But the other side, which consists of the spheres, uses a VDB. So first of all, I think we've actually covered most of this now in tutorials. First of all, we randomly change the size of our input sphere. So we've got something that's a little bit closer to the size of the canopy that we want. And then we take, at this point we could scatter points on them, but I haven't even bothered to do that. I've just taken the actual points that exist on the surfaces of those spheres. and I've copied a new sphere to each of those points. So you can see now we've got a bunch of spheres all sitting on the points and all blending together. And at the moment we've got the inside of all those spheres inside the tree, which is really not what we want. So we use a volume to get rid of that and to simplify it. So exactly as we just did, we create a surface VDB from polygons. So that's smoothing everything out and removing the interior of our tree. And then we convert it back again. And we keep our voxel size pretty big relative to the tree. So we're getting something quite low res coming out again. And then we probably reduce it to drop it down even more. We add a slightly randomized color to it, and the same for the trunk, and bring them back together again. And that's basically it. We use our random seed, which is promoted to the top of our digital asset to change the shape of the L system. So that has some randomness in it. So we're getting different shapes to start off with. And it also randomly changes the colours. So you can see the VDB for optimization, and in this case not just optimization, but in order to achieve a certain kind of style. You can see that in action in the tree. Next, let's take a look at some of the ways you can manipulate volumes. I'm just going to look at this very quickly. There's a lot of different nodes in there that will do different things, and we'll look at them at a later date. For now, I'm just going to look at the volume VOP, which is a variation on the attribute VOP, which you've seen before. So let's create another geometry node. I'll just go straight to creating a sphere, and we can work with that. I'll make this a polygon. Up the frequency a bit, but you don't actually need it to be that high, because as soon as we convert it into the voxels, it's the size of the voxel that counts and not the frequency of our polygons. Okay, so once again we drop down a VDB to polygon, VDB from polygons. But this time, instead of creating a surface VDB or a distance VDB, which is the signed distance field, we're going to create a fog VDB. And this creates a voxel for every point inside our volume, which is probably what you would think of when you imagine voxels. Now, next thing I'm going to do is drop down a volume VOP, and you can use these either with VDBs or volumes, which is nice and flexible. And before I start playing around with it, I'm also going to put in a convert VDB and convert this back to a surface again, because it's a lot easier to see what's going on when you're looking at it as a polygon. So here we go. Oh, for some reason that's not creating anything. Could be our ISO value just needs tweaked. I find quite often you do need to adjust that slightly. I think it's probably something to do with it being a fog VDB, and we need our surface to be slightly offset from the fog. Probably make that very low value. And I'm going to reduce our voxel size so we've got a bit more density. So we've got quite a smooth sphere now. And let's open up our volume VOP. So you'll see this is very similar to the attribute VOP, but you have a different set of inputs. Most of the time you're going to be working with your P value, which is the position of all the voxels inside your volume, and your density, which is the value of each of those voxels. Now, because we've only created voxels inside our sphere, we're only going to be working inside this existing sphere. And we're going to add some noise to it till you see what happens. So our noise nodes are exactly the same as in an attribute VOP. So I'm going to drop down some anti-alias noise. This, for some reason, the volume VOP doesn't seem to be very good at hooking things up to the right places. So what we actually want is our position to be connected to P, and you can see immediately that we've created noise. If you were doing this with a surface, then you would see the noise affecting the surface, but you wouldn't see it cutting all the way through in the same way. So if you're looking for effects that actually smash through objects, then this is the way to do it. I'll just quickly play around with it a little bit so you can see what you can do. All the settings are exactly the same as you would get in a normal VOP node. And if we go out and just look at the volume, you'll see why I put the surface on, because we're dealing with potentially quite low values of density and it's quite hard to see what's going on. So it's much easier if you can see the surface. Back in. Another noise that I find looks quite nice is the curl noise. So once again, we hook up our position and we put our output into the density. We're getting quite interesting swirly effects that cut right through our object. And if you play around with patterns, you can find this could be a nice easy way to create some interesting shapes in the same way that you would create Boolean shapes. So a lot of the patterns use UVs, but if we hook them up to the P attribute, it'll use the X and Y values for UVs. So you can see we're getting some quite interesting shapes in there. So this is just giving you a little taster of what you can do with your volumes once you've created them. I'll call that volume manipulation. The last thing we're going to look at is replacing voxels in a volume with blocks, which allows you to create a version of your geometry that looks like it's built out of blocks. This is how you'll have seen images in Houdini of objects made out of Lego. So to demonstrate, first of all, I'm going to load up the pig's head again. So I'll go back to the test geometry, turn this off, and to start with we can use we probably want to use a fog volume, so the same as the last one we were looking at, but you can use any kind of volume or VDB for this. So let's do a VDB fog. So we'll do a VDB from polygons. And we'll make it a density VDB. And then we use a node called VDB Visualize Tree, and this does a lot of things, but one of them is it allows you to create a point at every one of the voxels. So here you can see we now have a collection of points. We want to select points, and we want to the points that have been created by our visualized tree don't currently have values on, but we can put a value on using points with values. So if we look at the geometry spreadsheet now and look at our points, we've got a value called VDB float, which should have both positive and negative values. Yeah, so it goes from about -3 to positive 3.3 rather. And this distance from the surface allows us to just select the points that we need near the surface. So we can first of all create a group where our, double check that, so this is called VDB underscore float. So we do at VDB underscore float less than 0. And you can see it's only selected the inside points, which are the ones that were white. So we can use a blast node to get rid of the rest. All this has done is got us back to where we were before with our volume node. But now, because we have a value to our points that reflects how far they are from the surface, we can get rid of the ones right on the inside as well. So if we do the same thing again, put in another group node, and this time do at VDB float is greater than, let's say, minus 0.1. Do we have any? Yeah, we should do. Oh, we're selecting primitives. That's why we're not getting that. There we go. So now we're just getting a band around the surface. So we can delete. Let's do a blast node again. And we do group 2 this time. And delete non-selected. And now if we do a copy to points, it should look the same, but the inside is hollow, and we're cutting down on a lot of the geometry inside it. if you have an object that sits exactly on the grid, you can be quite precise about how you fill it in with blocks. So I'm going to load in a file that I've created, which consists of some small houses which are built exactly to the grid. So here you can see these almost look like they're made of blocks already, but in fact they're just flat polygons that are subdivided. So there's nothing inside them. And obviously the roofs are still curved. So once again we'll go to create a volume, but in this case we want to create a volume rather than a VDB, because as I mentioned at the beginning of this tutorial, by using a volume you can get each point created exactly inside the number of subdivisions that your volume's divided into. So it's easiest to demonstrate. So I want an ISO offset node to create a volume, and our squares on these houses are 0.1, so we're going to create voxels that are the same size. When you're creating a volume, the default is to give you the size of the axis. It's much easier to do it by size, which is similar to the way that you would set up a VDB. So this defaults to 0.1, which is what we want. It actually looks quite nice already. You can see the shape being built up by the cloud. And now I'm going to turn this into a VDB. So we want to go back to our convert node, which we use for just about everything. So we have our convert VDB. The reason I'm doing this is because the VDB visualized tree is only available for VDBs. So we need to create a VDB out of this. We'll just leave it as a fog for now. And then we want the VDB visualized tree node. And we'll display our voxels as points. And if we switch on our original file, you'll see now each point sits exactly inside the box. If we were to create a VDB from polygons and do the same thing with it, you'll see, if you look at the white dots, you'll see they sit on the lines, which is not what we want. And then all you need to do is replace these. So I'm going to create another cube, and again we'll make it 0.1. Make it a little bit interesting by beveling it. We've got very simple bevels, and I think probably fix the normals on that as well before we do anything with it. So we've got some hard edges now as well. And then we use our copy to points node. And you can see I have a new copy with my domes all recreated in cubes and everything all lined up to the grid. If go back to the original file, you see it sits in exactly the same place. I'd also like my colours on there, so I'm going to use an attribute transfer node. There's a slight problem here because the points created by VDB visualized tree are red, and they're transferring their color onto copy to points, which is not what we want. So let's exclude our color from our points. So now they're white. The reason we're doing this is because if you have points that have a color per point and a color per primitive, the color per point will always override it. And our original model here actually uses color per primitive. So when we try an attribute transfer, it will correctly color all our blocks with the nearest primitive color. Okay, I'm going to leave volumes for now because we've covered quite a lot already. I'll come back and look at individual nodes at a later date. And I'll share this file with you so you can have a look at it, and also the previous file I showed you, which has ideal paths for different situations. And I'll also share that as a cheat sheet so you can look it up easily. I'm going to be on holiday in a couple of weeks, so probably not going to fit in another long tutorial before then. I might try and line up a few short ones and look at some of the simpler nodes. Please subscribe and come back again for the next tutorial.